Stream calculations. In this video, we will do example problems for calculations you can expect to do while in an intro geology lab on streams and surface water. So we will calculate stream sinuosity, which is a measure of how essentially curvy a stream's channel is in map view. We will also calculate discharge, which is the volume of water flowing through a stream over a given amount of time, and flood recurrence, which is a bit confusing when you hear the names we give, like 100-year flood, 200-year flood, versus what we actually mean. But that one will make sense when we take a look at it towards the end of this video. So the first calculation that we're going to make is stream sinuosity. For stream sinuosity, you see that we will be measuring on the map the actual length of the stream versus the straight line length. So what I'm going to do is I'm going to highlight and draw what we're going to measure on the map so that we can see it a little bit more easily. So the actual channel length I'm going to highlight in yellow, which is not going to show up too great on this map, but will hopefully help you see it a little bit easier. And then the straight line length I'm going to draw using a ruler with a red marker. So the actual channel length, you can see that I've highlighted. We're going to follow the stream as it goes with a string so that we can then straighten that string out and measure its length. And then the straight line length is just straight from A to B with the ruler. So the first thing, the actual channel length, you want to get a string and you want to move and bend the string so that it is following the channel along its path on the map area. And then what we're going to do once we get this all the way from A to B is we're going to take and straighten it out and measure its length with our ruler in centimeters. Now your number might be a little bit different because your map is a slightly different size, but mine, being a larger image, has a very large number. So for mine, we are looking at about 42.8 centimeters. So we write that in what will be the top of our fraction, and then we have to take the straight line length, so measuring with our ruler from A to B, straight along that line, and when I set that on here I get 13.6 centimeters. Now again, your numbers might be a little bit different because your image is a smaller size. What we do now is we are ready to go ahead and plug this into our calculator. So we take 42.8 centimeters divided by 13.6 centimeters, and we see that our sinuosity is 3.15. Now what that means for the sinuosity of a stream is we're looking at a meandering stream, and as you can tell there's a lot of curvature to the stream in this map area. The next calculation that we're going to perform in this video is stream discharge. Again, stream discharge is the volume of water flowing past a point in a given amount of time. So to calculate stream discharge, we need to calculate velocity, distance over time. So we have 2 points along the stream, A and B, that we have measured, or we can measure the distance between. And we throw something like an orange that floats in the water so we can time how long it takes the orange to go from A to B along the stream. The cross-sectional area of the stream, as you can see in this image, is looking at the stream from the side. So imagine the water's flowing out of the image towards you. So we make some assumptions at the introductory level that the stream channels match a nice geometric shape, like a circular shape or a rectangular shape. So let's go ahead and look at a sample problem, and it's going to be a word problem. So An orange is thrown into a stream and floats between 2 points 60 meters apart in 3 seconds. The stream has a rectangular shape in cross-section with a width of 10 meters and a depth of 5 meters. What is the discharge in cubic meters per second? So let's go ahead and write our equation. Q equals V times A. So, first thing that we want to look for in the word problem are things that are going to help us calculate velocity. So we're looking at a distance along the stream over time. And we find that in the first sentence. 2 points are 60 meters apart and the orange floats between them in 3 seconds. So I'm going to go ahead and highlight those. So we know when solving for velocity, looking at what we've been given, our distance is 60 meters and our time is 3 seconds. So I'm going to write d over t, and we're going to set that equal to 60 meters over 3 seconds. So when we plug this into our calculator, or you might be able to do this in your head, 60 meters divided by 3 seconds is going to be 20 meters per second. Now, we need to figure out, do we need to do anything else to the number we got for velocity? Because we might need to convert the units. So we look at what the answer is supposed to be given in, cubic meters per second. That means anything that has a measure of distance needs to be in meters, which our number is, and anything that has a unit of time associated with it needs to be in seconds, which our number is. So we are ready, since our units are the same as what the answer is being asked for, we are ready to put the velocity into the equation for discharge. So Q is going to equal 20 meters per second times what we need to figure out for the area. And what we're told about the cross-section of the stream is that it has a rectangular shape. So I'm going to highlight that. And we are given information about the size of the stream. The width is 10 meters and the depth is 5 meters. So we'll highlight both of those. So the equation that we're going to use for the area is, in the terms of what we've been given, the width times the depth. Because it's a rectangle, so we're going to look at the width of the stream times the depth of the stream. So we have a 10 meter width times a 5 meter depth, and when we multiply those, we find that the area is 50 square meters. So, because we're looking at a unit that has a distance associated with it, it's squared because it's an area, we're in meters, which is what we want our answer in. So we are ready to plug this number directly into the equation at the top. So we have 20 meters per second times 50 meters squared, and when we either plug that into your calculator or do it in your head, plug it in your calculator is a good double check, we see that the discharge along the stream is 1,000 cubic meters per second, which are in the units that the answer was asked for. So that's all we have to do for stream discharge. The last calculation that we're going to do in this video for streams is the flood recurrence interval. Now, this one again, when you find the flood recurrence interval, it'll be something like the 100-year flood. Now, when you hear somebody say that was a 100-year flood, intuitively you think that means the flood happens every 100 years. That's not at all what we mean when we say the 100-year flood. What we're going to do is some math and calculations to figure out what does something like the 100-year flood actually mean. So the equation we're going to use is up here, where we're looking at the recurrence interval equals the number of years on record plus 1 divided by the rank of the flood. So Looking at the data that you're given, the rank of the flood works like this. The largest flood, which means the river's highest elevation recorded in your data set, gets a rank of 1. Then the next highest flood gets a rank of 2, and however many you have in your data set, you keep adding a number up for each one. So the biggest flood is 1, and then smaller floods get numbers corresponding to that are higher. So we have our floods ranked 1 and 2. To figure out the recurrence interval, we use this equation. So number of years on record we're given right here as 99. So we're going to take 99 and we add 1 from that equation, and then we divide it by the rank of the flood. So I'm going to write that out for both of our floods in our data set. So we have 99 plus 1, which is 100, divided by 1, 100. So recurrence interval for the first one is 100 years. 99 plus 1 divided by 2, 100 divided by 2. Our second one is our 50-year flood. So we have the names 100-year flood, 50-year flood, but what do they actually mean? That's where we're going to do the last column. What you write in the last column is 1 in for both of these, and then the number for the recurrence interval. So 1 in 100, because this is our 100-year flood, 1 in 50, because this is the 50-year flood. To figure out the percent, you just divide 1 divided by 100, 1 divided by 50. When you do that, 1 divided by 100 gives you an answer of 1%, and 1 divided by 50 gives you an answer of 2%. So what this actually means when we say 100-year flood, we're saying the likelihood of having a flood this large, as our first one, in a given year is 1%. So if you look at every year, there's a 1% chance of having a flood this large. After 100 years, you've had 1% plus 1% all the way up to 100. You should have a flood this size within a 100-year time period. There are instances, however, where there have been back-to-back years with 100-year floods. Looking at the 50-year flood, there's a 2% chance that a flood that size will happen this year or any year in record. These are some of the calculations that you can expect to make while doing a streams lab in an intro geology course.